Controllo di nuovo, sì, c'è già il tastino.
Ci siamo.
Ok. Tutto tuo.
Grazie.
Sì. Aspettiamo un attimo. Intanto vi presento il professor Gallo. Allora, intanto grazie ai ragazzi di essere venuti perché allora loro sono studenti.
Ok.
Io non sono ancora laureata. Adesso lo presento in italiano, poi in realtà il seminario sarà in inglese, sì, perché lui è stato con noi, ha fatto il dottorato qui con noi nel 2000 e...
Cominciato nel 2005 fino al 2009.
Esatto, quindi ha fatto il dottorato di ricerca in cotutela tra la nostra università e l'università brasiliana che è l'università di Campinas. Poi è tornato in Brasile, ha passato un periodo di 3 anni agli Stati Uniti, all'università di Madison, e adesso ha un posto come professore all'università di San Carlos in Brasile. Quindi si occupa di fatto di preparazione di catalizzatori eterogenei per applicazioni di conversione di biomass specialmente, quindi questo sarà il topic del suo talk di oggi. Quindi l'abbiamo invitato perché ovviamente siamo molto contenti che lui sia qua venuto a trovarci, perché abbiamo passato con lui tanto tempo, e anche un esempio di quello che è appunto il fatto di poter studiare, di poter crescere le proprie conoscenze, può fare, perché lui è molto giovane, ma ha già una posizione appunto da professore all'università, quindi è con grande piacere che appunto oggi lo accogliamo qua. Per cui adesso io farei così, aspettiamo magari ancora qualche minuto, vedere se arriva il professor Marchese, poi possiamo cominciare. Lui appunto gli ho chiesto di fare un seminario, visto che siete un po' eterogenei, perché abbiamo dei professori, ricercatori, dottorati e studenti, fa un seminario un po' partendo dalle basi di quello che è la conversione delle biomasse e poi relativo ai suoi risultati più recenti. Quindi...
aspettiamo.
Aspettiamo un attimo. Poi le domande ovviamente sono
in italiano va bene.
Potete fare in italiano, così siete più stimolati. Ha rivisto con piacere l'università, ha detto che non ha cambiato quasi niente.
No, quasi niente.
Un po' sì, dai.
Va bene. Sì, le facce sono diverse però. Meno male. No, c'è la sua. Ma abbiamo cominciato insieme? Ah, ecco. Io ho fatto l'esame il 2005, mi sa, novembre.
Perché non so se avevo fatto l'esame io?
Lui iniziava.
Iniziavo il dottorato.
Io finivo.
Ecco, no, facevo l'esame di ingresso.
Che hai fatto qua?
Ho fatto qua.
Però poi hai discusso in Brasile.
C'era ancora la serie vecchia. Mi sa che abbiamo fatto no?
L'esame.
Ecco.
Era location più indicato.
Poi eravamo troppo matti. Ho detto no, qui non va bene. Dimmi tu. Allora, è anche meglio se non uso il laser, perché in streaming non si può vedere, né?
No, sì, infatti.
Quindi niente. Cosa faccio? Niente.
Così.
Quel mouse no, non funziona neanche.
Cosa ha detto? Usi il microfono?
No, il microfono è qua, quindi deve stare vicino al microfono.
Non ti sento, non ci parli, non ci alza.
Sì.
Quindi iniziamo.
Va bene. Vado? Ok, grazie Chiara. È veramente un grosso piacere stare qui dopo 8 anni, mi sa. Ho finito la mia tesi nel 2009, quindi è un piacere speciale parlare qui ad Alessandria. La mia presentazione la faccio in inglese, come ha detto già Chiara, perché ormai ho 8 anni che non parlo italiano, forse è meglio l'inglese. Today I'm talking about heterogeneous, the design and synthesis preparation, and mainly the design of heterogeneous catalysts for the chemical conversion of biomass. So we start today with a very quick introduction, so you have an idea what biomass is. And then I'll show you what are the problems involved in the biomass conversion, the catalytic conversion of biomass. And then what we have done to solve, or to try to solve, or to bring new ideas to solve these problems involved on biomass conversion. So nowadays I'm a professor in inorganic chemistry at the Federal University of São Carlos back in Brazil. But now I'm at Friedrich Schiller University of Vienna in Germany for 1 year as a guest scientist. So I'll show you first where I live. I'm in São Carlos. This is the map of Brazil. So giving a zoom, we see São Carlos is a small town for the Brazilian standard, 220 about 1,000 people there. About 50% of the people in the university are somehow correlated to the university, staff or students. We have 2 of the very big universities in Brazil. So our university is pretty young. It was founded in 1970. For European standards, this is a baby, not even born, maybe. It's a very young university, but we are already the 3rd best PhD course or grad school in chemistry in the country. So this is a brand new release. We were selected as the 3rd best PhD school in chemistry. And we are also the best young university in the country and the best federal university outside the state capital. So it's a university that's growing a lot. We have 4 campuses. This is or 4 campi. This is the main campus, which is pretty big. We have 6.5 million square meters of area. And this is a preservation area you can see around. This is the Brazilian savanna. It's a very special place. And almost 200,000 square meters in building area. So that's the main university, the main campus. And these are the players. Those are my students. There's Priscilla, who's a postdoc, Tainara, and Pedro, PhD students. Eduardo is a master student getting to the PhD soon. He's defending really soon. And then Juliana, Natalia, and Jose Lucas are the undergrads. They're pretty close to finish chemistry, and hopefully next year they will be master students as well. I'm very proud to say that all my students, even on those times that money is not easy to get, all my students are funded with fellowships, even their undergrads, so they can spend a good share of their time in the lab. So, going back to science. Since you don't have such a large background on biomass conversion, I want to talk to you a little bit about chemical industry and biomass. First thing is try to understand what's going on in chemical industry. I'll give you a couple of examples. When we look to a plastic bottle, this plastic bottle, we buy water on it. It's made of polyethylene terephthalate, which is a polymer of terephthalic acid and ethylene glycol. To make it simple, where these compounds came from, I'm making a shortcut. I'm not showing all the processes, just some of the major precursors. So terephthalic acid comes from paraxylene, and ethylene glycol from ethylene. And where do we get them? They all came straight from refinery, from the petroleum. When we talk about fuels, they're basically a mixture of hydrocarbons that come from petroleum. And a medicine, let's say Tylenol, a common one, we take it all the time. So paracetamol is prepared by the synthesis, one-pot synthesis of these 3 compounds. Just to give the example of the phenol. The phenol, again, there are several processes involved to make the phenol. I'll show 2 of the intermediates. Benzene, it comes from benzene, that comes from toluene. And toluene, again, comes straight from the petroleum. Nowadays, chemical industry, if I want to make fuel, plastics, or even medicines, I do need the petroleum. Our chemical industry is based on petroleum and natural gas. So basically, worldwide, we can say that about 80% of the fuel and 95% of the chemicals will come from petroleum or natural gas. Back in Brazil, these numbers are different, okay? Basically, 1/3 or even more of the fuel is bioethanol. Here in Europe, you also use bioethanol. I haven't filled my car here in Italy yet, but in Germany, we have 5% and 10% bioethanol in the fuel, in the gasoline. So, but in Brazil, we use pure ethanol as a fuel as well. So what are the problems involved in having a chemical industry based on petroleum? Petroleum is not ending. It's not. We have a lot of petroleum. The deal is that the extraction now, it's being done in less accessible areas. Let's say in Brazil, for instance, we are getting the petroleum really deep in the ocean. That's expensive petroleum. The other thing is like processing. We have to process heavier fractions. If the fractions are heavy, we have to break it. It's the cracking. We spend more money in the hydrocracking. And the other problem is more political, which is, for instance, the fluctuation of prices. The petroleum can go to $200 a barrel. Now it's 50, and we don't know what's going on next. And also the political use. So here in Europe, sometimes you hear when there are problems involving Russia, they have a lot of natural gas. They use that as a exchange coin on political discussions. So having the petroleum, natural gas, having the industry based on this petroleum, natural gas do present problems. And what would be the alternative? Because you guys still want your plastic bottle. You guys still want to have a fuel in your car. You're not riding a bike all the time forever. So, and you also want medicine. All these common products, daily products, they derive from petroleum. So one alternative would be the biomass, vegetables, whatever comes from nature. And two examples here are the sugarcane and the sweet corn that are used as renewable sources for making chemicals. What part of those do we use? It cannot be edible. Food first, chemical second. So we're not stop eating to make fuel. So we have to use things from vegetables that are not edible, that we do not eat. So the idea is using, for instance, let's say the sugarcane, we use the bagasse. From corn or sugarcane, the harvest waste, whatever remains, or the corn cobs, let's say. So then can get complicated because petroleum is a black liquid. That composition is hydrocarbons. Now, what I'm proposing is that why don't we use, let's say, bagasse, harvest waste, corn cobs? This can get complicated, but because one can say, look, they look different, they taste different, they smell different. Their composition is probably really different. So it would be really complicated to make these things into chemicals. Actually, the composition is really simple. No matter how they look, how they smell, how they taste, the composition is always very similar, or the components are very similar. Most of these sources, they are based on lignin, hemicellulose, and cellulose. Lignin is a polymer of phenols. Hemicellulose of a polymer of monosaccharide named xylose, mainly. Other monosaccharides can be there too in this polymer, but mainly xylose. And cellulose is a polymer of glucose, which is a sugar we all know. So that's the major composition. It's completely different from petroleum, but still, it's not that complicated. What can we do then to transform these molecules into chemicals and fuels? We have to think of what is really important. These three components are the most important ones. But in my opinion, the very important ones are the monosaccharides, which are basically 65 to 85% of the plant composition. And we work mainly in the cellulose fraction, which is basically 50% of the plant composition. We also work in the hemicellulose, but today I'll focus more on the cellulose fraction. Okay, so how can we transform this thing, this vegetables, this whatever comes from nature into chemicals? How can we do that? How can we make this chemical conversion? So I told you that we have mainly hemicellulose and cellulose. The first thing we can do is depolymerize the cellulose into glucose, as a sugar, monosaccharide. So what you can do next is transform, is an isomerization reaction, transform glucose into fructose, another monosaccharide we all know. And then we can use a catalyst, proton, acid catalyst. Can get simpler, can get easier. Just acid catalyst. We can transform fructose in this 5-hydroxymethylfurfural, the HMF. That's the nickname, HMF. And HMF can be also transformed to livolinic acid. For the hemicellulose, very simple, very similar actually. Hemicellulose, we depolymerize into xylose, then acid catalysis for furfural. We can also make furfural alcohol that can be then converted to livolinic acid. Another option is to take the sugar, sucrose, or the cellulose, and make a fermentation to produce ethanol. Ethanol we all know. These molecules in blue, with blue background, they are named platform molecules. They are named platform molecules because they are platforms. They can be converted in many other molecules, in many other important molecules. HMF, livolinic acid, furfural alcohol, furfural are platform molecules, and ethanol are platform molecules. Except for ethanol, all the other ones do not have a very large application in the industry. Very small application, few thousand per year produced. So they're not commodities. Ethanol is important as a fuel, but all of them can get even more important because they could be converted into chemicals and fuels. And how do we do that? Let's start with one example, a molecule that I like a lot, the 5-hydroxymethylfurfural HMF. So this slide is really complicated. Don't try to understand everything. So you can follow me. I'm using each arrow will show a catalyst and then a product that I can make out of HMF. So let's say the first example, dihydroxymethyl THF. This is a precursor for polymers and solvents. Let's say this huge molecule here, 1,5-difuryl, 1,4-pentadiene trione. This molecule can be made by the aldecondensation of 2 HMF molecules and 1 acetone. If I hydrogenate this molecule, after all, I have the decapentane. Decapentane can be used as a fuel. And I'm showing decapentane in red. All the molecules I'm showing in red are molecules that I get from the petroleum as well. The molecules that I'm showing in black, they are produced only from biomass. Then from HMF, I can also make 2,5-methylfuran hydrogenation reaction. 2,5-methylfuran can be used as a fuel as well. Different one, a different fuel, but it can be used as a fuel. Let's say I can get the paroxylene. Should be in red, actually. Paroxylene I get from petroleum, but I can also get from biomass. And then I can oxidize this paroxylene to make terephthalic acid, which is used to make plastic bottles. There's another option. I oxidize 5-hydroxymethylfurfural, HMF, to 2,5-furan-decarboxylic acid. Look how much this 2,5-furan-decarboxylic acid is similar to terephthalic acid. They're very similar. There's a ring in the middle, and it's diacid. So this molecule can also be used to make plastic bottles that people call bioPET, which is an alternative for the PET, the plastic bottles we use. So the message from this slide is that out of HMF, I can make new chemicals. I can also make chemicals that are usually obtained from biomass, from petroleum. I can, let's give the example of terephthalic acid and 2,5-furan-decarboxylic acid. One can be obtained from petroleum to make plastic bottles. The other one can be obtained only from biomass to make plastic bottles. So I can make the traditional plastic bottle or a biorenewable plastic bottle. We could give the same example for furfural. Here we can go faster. just to show you that out of Furfural, I can make chemical modifications to make plastics, to make fuel, to make chemicals. And we can say the same about ethanol. We love ethanol in Brazil, back in Brazil. Not only for drinking, but also to make chemicals and fuel. So we use ethanol as a fuel, but we can also work with ethanol to make ethylene, acetic acid, butadiene, aromatics, and all these chemicals that usually, hydrogen is highly important. All these chemicals that are usually obtained from petroleum. So the message here is that biomass can be really powerful to bring the same products that we get from petroleum, or even new products with same application. So this is the overall picture. So the idea here is try to convince you that biomass can be used using the right catalyst. Biomass can be used to produce important chemicals. But so why don't we have yet a biorefinery, which means a refinery that uses biomass? Why don't we still have, why we don't have yet a industry that converts biomass or plants or whatever remains in the field into important chemicals in fuel? We do have for ethanol production as a fuel, but not for making chemicals, because there are a lot of problems involved that need to be solved. The chemistry on converting biomass into chemicals need to be improved. So I point out 4 of the big problems in processing biomass. And these 4 points were raised in a European report that was published a couple of years ago. And they were pointing what are the problems in biomass conversion. And 4 of the major problems in processing biomass are that we need corrosive substances, mainly mineral acids as catalysts. I showed you some slides back that we need protein to convert biomass. And protein are usually mineral acids. Those are the traditional catalysts. So this is a problem. The second, the yields, the amount of chemical products that I get from biomass is still not enough. I have to improve the yields. I have to be able to make more out of the biomass. So this is yield. So if I get 1 kilogram of biomass, I want to have at least 1 kilogram, the ideal 1 kilogram of product. But we still can't do that so efficiently. And then we need to design better processes, better catalysts. And we have to integrate process, which is make a lot of reactions in the same reactor. I put my biomass inside and get, at the end of my reactor, a product that I really like, really expensive. I don't want to make several reactions in several different reactors. I want like magic, put my biomass here and take my product at the end. So the more reactions I can make inside one single reactor, the better is my process, because I don't have to deal with separation, purification of each and every step. And how can we solve these problems? So we can use catalysis. We can study catalysts to improve the biomass conversion. And we can work with catalyst stability, make my catalyst more stable. We can replace the mineral acids, which are homogeneous, by heterogeneous catalyst solids. We can design better catalysts. We can work in one pot regime. That means making a lot of reactions inside one reactor. And I can also design multifunctional catalysts. One catalyst that can make several reactions. That would be ideal. So I picked 2 examples for you guys. One, the synthesis of HMF, and the other one is the direct conversion of ethanol into acetate. And in each of them, we will discuss what we have done to improve, in the first example, catalyst stability, replacing homogeneous catalysts for heterogeneous ones, working process to make one pot regime, and also to produce bifunctional catalysts. In the second example, the same issues, bifunctional catalysts, one pot regime, and how we work in the surface chemistry to understand the reaction mechanism, or the reaction pathway, actually. So let's start with the synthesis of HMF. I showed you this before. So from biomass, I go to glucose. From glucose, I isomerize to fructose. And from fructose, I use a Bronsted acid, proton, to make HMF. If I try to make HMF directly from glucose, my yields are really low. So 30% or below 30%. That means that if I get 1 mole of glucose, at the end I have less than 0.3 moles of HMF. So I'm losing a lot of carbon. I'm losing a lot of my reactant. So what we can do then is convert from fructose, make fructose and convert into HMF. So for every mole of fructose I use, I get at the end at least 0.7 mole of HMF, which is good, 7% yield. What is the problem in converting fructose into HMF? The catalysts have very low stability, which means that the water that is in the reaction, and biomass is always wet, so I always have water, it hydrolyzes the acid group in my support. So the acid group goes away. So my catalyst stops working, has low stability. The first thing we have done, it was a proof of concept. We got a porous silica, and inside the pores of the silica, we put a acid group, propylsulfonic acid. And this catalyst has very low stability because this acid group will be hydrolyzed. It goes away. It leaves my support. So what we did was reacting the surface of the silica with polyvinylpyrrolidone, which is a polymer. So what I have inside the pores are the surface of silica with my acid group and polyvinylpyrrolidone covering the surface. So the water cannot get close to the surface of silica, so it doesn't let my functional group, my acid group, to hydrolyze. So we saw that we can increase the stability of this catalyst by putting PVP, polyvinylpyrrolidone, by 2.5 times. But actually, we were looking for stability, but we found something else. We found that when we make this catalyst, we increase the selectivity of the catalyst by 30%. It's a lot. We increased by a lot. And we couldn't understand why that was happening. So we made an in situ study with NMR. And what we learned is that fructose is mainly on the fructopyranose form. There's one with 6-member ring. When the fructose meets the PVP, the polyvinylpyrrolidone, the equilibrium shifted, and they start producing fructofuranose, 5-member ring. So the equilibrium is shifting for the fructopyranose. And the fructopyranose, the fructofuranose, 5-member ring, is dehydrated to HMF. It seems that the fructofuranose is dehydrated to HMF with higher yield than if I dehydrate the fructopyranose. So besides increasing the stability, we were able to increase also the selectivity. This is a work from 2003. There's a more recent one from last year. That what we did was this is the scheme on how the material was synthesized. But I want you to look these two compounds here. Okay, CMK3, CMK5. Those are carbons. Carbon structure, porous carbon structure. So we prepared these two carbons, and these carbons, they don't have functional groups on the surface. They do nothing. Okay, it's just carbon and hydrogen. So what we did was reacting the surface of these two carbons with these groups I'm showing you there, this phenyl sulfonic acid and the naphthalene sulfonic acid. So at the end, first catalyst, I want you to look the last row, deactivation rate constant coefficient. The lower is the deactivation rate constant, the more stable is the catalyst. Means the lower it is means that it deactivates less. So our catalysts will show deactivation rate constant between 1.4 and 9. When we look the catalyst that I showed you in the previous slide, the silica with prosulfonic acid, the activation rate constant is like 120. So at least 20 times higher than the carbon catalysts. So they're at least 20 times more stable than the catalyst I showed you previously in the previous slide. And the catalyst we prepare here can be even more stable than the commercial catalyst, that is this Nathan SAC13. So because we have carbon-carbon bond between the surface and the functional group, this catalyst become really stable. Okay, but so we helped solving the stability problem and converting fructose into HMF. But fructose is really expensive because it's obtained from glucose. I have to isomerize glucose into fructose. So fructose is 2 times more expensive, at least, than fructose is 2 times more expensive than glucose. Would be awesome if I could convert glucose directly to HMF. But I showed you before that this can be done with very low yields. Can we do that somehow? So what we did was proposing a new catalytic or catalytic system using 2 catalysts. One is a metal oxide, a metal chloride, and the other one, HCl acid. What we learned is that glucose, in the presence of a metal chlorine, can be isomerized to fructose, and fructose then is dehydrated to HMF. And then we get, when we use, for instance, aluminum chloride, we can get 68% selectivity from glucose, directly from glucose, 68% selectivity for HMF, which is really great. From fructose, we can get 80 maybe, but still, glucose is 2 times cheaper than fructose. But here we have a problem. We have homogeneous catalysts. Everything is in solution. And I have HCl. I told you before that we don't want to use mineral acids. So what we tried to do was trying to replace this homogeneous catalyst by heterogeneous catalysts. Can we make a solid acid, solid Lewis acid, solid Bronsted acid? What we are doing now, for instance, is trying to work with niobium phosphate. And why niobium? Because Brazil has 98% of the reserves of niobium. So we love making research of niobium. If you can find alternatives to use niobium, is great for the country. So what we did was niobium phosphates, and we learned that niobium phosphates, and this is José Lucas, my undergrad student, who is making this work. And we learned that niobium phosphate is bifunctional, has both Lewis acid and Bronsted acid. And what we see is that when we convert glucose, it forms a lot of fructose, so it's good Lewis acid. But I don't form much of HMF, the blue bar. The selectivity for HMF is low. So this niobium phosphate is a good Lewis acid, but a bad Bronsted acid. We tried then to use niobium oxide, and phosphonate the surface of this niobium. And what you see on the left is that when we buy a commercial niobium and we phosphonate it, the conversion is low, selectivity for fructose is low, selectivity for HMF is low. So this is not a good catalyst. But when we make the niobium oxide ourselves, we see that the activity is pretty high, the selectivity is much higher for fructose and also for HMF. So we were able to make, or José Lucas has been able to make catalysts that are fairly selective for fructose and HMF. Catalysts that are bifunctional. They are able alone to have Lewis acid and Bronsted acid. They alone can catalyze 2 reactions: glucose isomerization to fructose, fructose dehydration to HMF. But the best result so far is using a combination of 2 catalysts. Tin beta, which is a zeolite with tin, and Amberley 70, which is a commercial acid resin. Tin beta is a Lewis acid. Amberley is a Bronsted acid. So when we mix them, we see in this graph that we start converting glucose, and then we start forming fructose, isomerization. And then fructose start being converted to HMF, dehydration. So a combination of these two catalysts are able to produce HMF with 63% yield, 70% selectivity. So we are getting the same results that we obtained with the homogeneous catalyst that I showed you before. So we replaced homogeneous catalyst by heterogeneous catalyst. We did not lose selectivity. But we can still improve that. We can still improve that. Team beta is really complicated to be prepared. So it takes like at least 15 days to prepare this catalyst. As far as I'm concerned, the syntheses are not very reliable. It's hard to reproduce the synthesis. So, all this turns this catalyst a little bit expensive. So I have two students, Eduardo and Juliana. These are Facebook pictures, okay? So that's why they're like posing like models. Anyways, so what we're trying to do is making amorphous silica easy to prepare and highly fast to prepare and cheap. In this specific case, they are making porous silica. We don't really care too much for pores, but those are porous silicas, and they're preparing several ones with different methods, different tin loadings, different pHs, and they're changing the condition. And what they learn is that when they prepare the silica with a hydroxide named tetramethyl ammonium hydroxide, they get pretty high activity for this catalyst. So you see that in the glucose conversion, the black bar, we get up to 40%. And I have to remind you that the equilibrium of this reaction is about 50%. So the maximum conversion I can get is 50%, because the equilibrium is around 50%. So we get pretty high conversion, and the selectivity is amazingly high. We can get up to 95% of selectivity. Here, for fructose, here we are only testing the glucose isomerization to fructose. Okay, so what we did was replacing the complicated tin beta by a easy to make tin silica, amorphous silica, and we can get basically the same results. So next step, obviously, would be to first understand why or how this amorphous silica can be as active as a tin beta. That's the first thing to understand. And the second, try to make HMF out of it. Try to modify this catalyst to put some bronzed acid and make HMF, our final product. So what I showed in these examples is that we could make a highly stable catalyst for HMF production from fructose. And then we could understand how to eventually move back towards the biomass and start converting glucose instead of fructose. And then we were able to create a homogeneous system that we could then improve to heterogeneous one. And then we can make a combination of two catalysts or a bifunctional catalyst. In both cases, we're moving toward the HMF using glucose to HMF using one pot regime. I put glucose, and there are two reactions happening inside the reactor: glucose to fructose, fructose to HMF. And so we're working one pot regime and making eventually even bifunctional catalysts. And we could also improve the complicated tin beta and make a easy to prepare tin silica, amorphous silica, with the same activity or similar activity. Chiara, how am I time-wise?
10 minutes.
I still have 10 minutes. Okay. So in the last 10 minutes, I will talk about ethanol direct conversion to ethyl acetate. And this is a good example to show how we can make a one-pot reaction using bifunctional catalysts and still understand the surface chemistry. This reaction is an oxidation reaction. I'm going from ethanol to ethyl acetate. I'm making oxidation, but I'm not using oxygen. Instead of adding oxygen, I'm making dehydrogenation. Ethanol is dehydrogenated to acetaldehyde, and acetaldehyde will suffer oxidative coupling with another molecule of ethanol to make ethyl acetate and produce 2 molecules of hydrogen. I love hydrogen. Industry loves hydrogen. So this reaction is interesting because they produce hydrogen, other than the ethyl acetate, which is an important chemical industrial solvent. Let's talk about surface chemistry. What is known, what is believed to happen, not known, but what is believed is that the ethanol dehydrogenation to acetaldehyde takes place in the copper surface. And the second reaction, the coupling reaction, takes place between the interface of copper and the support, zirconium oxide. So first reaction, only in copper. Second reaction, in the interface. Acetaldehyde is activated by copper, and ethanol is activated by zirconia, and the coupling reaction takes place in the interface. So our question was, is that really true? Do we really need the interface? So that was the work by Pedro and Tainara. Again, Facebook pictures. They will hate me for that, probably. They are not here, doesn't matter. So again, we prepared mesoporous silica, which are model supports. We can control the supports. And inside the silica, we put the copper. Inside each pore of the silica, we put a copper inside, a copper nanoparticle inside, small nanoparticles. And then we add different oxides: aluminum oxide, chromium oxide, zinc oxide, and zirconium oxide. And then we have at the end 5% metal oxide, 10% copper on MCM41, which is this mesoporous silica. So what we see is that no matter the catalyst we prepare, we still have the porous structure. That's okay. But what I want you to look is the second table, this table. When we have 10% of copper, the dispersion of copper is 25%. So it's quite dispersed. It's well dispersed in the pores. When I add the oxides, I see that the dispersion goes down. 90%, 8%, 7%, 11%. So we try to understand why that was going on. And what we figured out is that it's lower dispersion could mean that the particles are getting bigger. But what we learned is that that's not true. I got these results 2 days ago, actually. I confirmed these results 2 days ago. So what we saw is that the particles are not getting bigger. What has happened is that my oxide is partially covering my copper nanoparticle. So it looks like my measurements will show me that it seems that the particles are getting bigger, but they're not. I have less copper exposed because the oxides I'm adding are partially coating the copper nanoparticle. What does that mean? That means that I'm creating an interface between my copper nanoparticle and the oxides. That's what I want, making this interface. And when I test these materials on catalysis, conversion of ethanol, there's the reaction on the side. What I see is that when I use 10% copper only, I form acetaldehyde. I make the dehydrogenation. But I just make a little bit of ethyl acetate, just a little bit, 2%. Poor selectivity. When I add zinc oxide, again, acetaldehyde, not much ethyl acetate. It's not helping. When I add aluminum oxide, that was horrible. No ethyl acetate at all. What I'm doing is making some acetaldehyde, but also ethyl wet ether, because aluminum oxide is acid, so it's making etherification. When I add chromium oxide, which is copper chromium, would be the commercial catalyst for this reaction. When I add chromium oxide, what I see is that the acetaldehyde selective is going down, and the ethyl acetate selective going up. So the acetaldehyde is being converted to ethyl acetate. Awesome. But just a little bit. The selectivity is increased from 2 to maybe 5 or 6%. And I'm also for methyl-ethyl ketone and one butanol that are products that I don't want right now. But when I add the best for the last, zirconium oxide, what I see is that the selectivity for ethyl acetate increases by a lot. It goes to up to 40%. So it seems that when I add the zirconium oxide, the coupling reaction is taking place. So we decided to study the turnover frequency. What does that mean? Turnover frequency, probably you don't know much about this term, but means the amount of how much of each side, how many molecules of ethanol, let's say like this, or actually how many molecules of ethyl acetate, the product, are formed for each side of copper in a unit of second. So per second, how many ethyl acetates are formed by this one side of copper? So the highest is the number, means that my side can make more ethyl acetate. So the highest the number, the more active is my side of copper. So what we see is that the copper, the 10% copper with no metal oxide is making 10 to minus 5 in the order 10 to minus 5 ethyl acetate. When I add the oxides, this number increases. So I'm making more ethyl acetate per unit of copper. And the best result by far is using zirconium oxide. I make 10 to minus 2. So I go from 10 to minus 5 to 10 to minus 2. So 3 orders of magnitude. So the rate of my reaction is increasing by 3 orders of magnitude when I add the zirconium oxide. So we figured that we could have 2 things going on. The first one, I really have the interface. And the second, the copper is producing acetaldehyde. This acetaldehyde is traveling to a zirconium oxide, which is really far from the copper, and the coupling reaction takes place on copper. Oh, I'm sorry, on zirconium oxide. So the copper makes the acetaldehyde. The acetaldehyde travels far, finds the zirconium oxide, and zirconium oxide is making the coupling reaction. So what we learned is that when we have only zirconium with no copper, so if you give to the zirconium ethanol plus acetaldehyde to make the coupling, when we give to the zirconium alone without copper, the reaction is 10 times slower than if I have copper. So the reaction happens in zirconium, in pure zirconium, but it's much slower than if I have the interface zirconium copper. So the takeaway message here is that the full reaction will happen in the presence of copper alone, copper and zirconia, one far from the other, and copper and zirconia close to each other. It happens no matter what. However, the reaction rate, the reaction gets faster when I have the interface. And if I have zinc oxide, chromium oxide, or zirconium oxide, the reaction will take place when in interface with copper. It takes place. However, when I have zirconium oxide, the reaction is much faster. I also, because I don't have time, I finish here, but we are working now on gold catalysts that we are able to fully understand the mechanism of this reaction. This is a brand new result, actually, happening now. We are writing a publication, so I won't have time to show you all. But that first copper example is where everything was born. So I thank FAPESP, which is FAPESP and CNPq, which are giving my funding for research, are paying my students. Alexander von Humboldt, which is paying my stay in Germany for the next year, and also the departments. And I finish with old-time pictures, maybe 8 years ago, 9 years ago. Yeah, from the group in a conference. I think there's almost everyone here. So yeah, this is young me in the somewhere there. Okay, I thank you all for the attention. Grazie.
bellissima presentazione, grazie. Ci sono delle domande?
Anche in italiano. Va
Anche in
bene.
italiano.
In italiano?
Sì.
Allora, la prima è sullo stagno beta, no? Poi hai detto che voi state facendo lo stagno silica. La silice è mesoporosa,
Sì.
quindi ha dimensioni più grandi rispetto alla beta che ha dimensioni
Ecco,
più
sì.
piccole. Non c'è un effetto delle dimensioni dei canali?
Allora, per la beta ci sono studi teorici, non nostri, che mostrano che la diffusione del zucchero, del saccharidio nei pori, non c'è limitazione di diffusione. Questi sono studi non mi ricordo come si chiama, vabbè, negli Stati Uniti. Quindi quello sì, dicono che non c'è, gli studi mostrano che non c'è limitazione di diffusione. Però secondo me, quando hai i pori più larghi, potresti avere una diffusione un po' più efficiente, nel senso che il grosso problema, abbiamo scoperto, c'è un nostro lavoro dal 2005 che mostra che più che la diffusione è la composizione del solventi che hai dentro dei pori. Allora, per la zeolita riesci ad avere una permeabilità diversa dell'acqua e del tuo solvente organico. Si lavora sempre con una miscela di acqua e solvente organico. Allora, il solvente organico ha una permeabilità più grande nella zeolita che l'acqua. Quindi dentro i pori hai una composizione diversa dei solventi. Mentre nel mesoporoso no, non hai questa limitazione, anche perché il mesoporoso ha una quantità enorme di silanoli, quindi la permeabilità di acqua è altissima. Quindi, quello che si vede in letteratura, non c'è limitazione diffusionale del zucchero nella zeolita. Quello, ripeto, quello che dicono i paper. Quello che sappiamo noi è che uno dei parametri più importanti che c'è nella conversione degli zuccheri è la composizione dei solventi dentro i pori. E questo cambia completamente il risultato della selettività. Ma certo.
Sempre sulla stessa reazione, mi hai parlato di un effetto sinergico acidità di Lewis e poi acidità di Bronsted,
Ecco.
che lavorano insieme. E quando hai parlato della stagno beta, quella fa l'acidità di Lewis, poi hai bisogno
di un acido di Bronsted.
Non avete mai pensato di provare materiali gerarchici, cioè quei materiali zeoliti, tipo una KZ-5 gerarchica, che hanno micromesopori? Se tu la rendi gerarchica, hai delle mesoporosità che la zeolite non ha, quindi la diffusione, tutte queste storie qui, ma hai siti di Bronsted e aumenti la quantità dei siti di Lewis che sono ad esempio l'alluminio subordinato.
Ecco, quello sarebbe bello, questi materiali, non con l'alluminio però, scordinato, perché l'ossido di alluminio purtroppo non è molto selettivo per l'isomerizzazione. Allora, le zeolite non sono buone per la dehydration di fruttose. Sono buone però per la dehydration di xylose. Quindi sì, quello andrebbe bene per la xilose. Come si dice in italiano? Xilose? Xilosi. Quindi quello andrebbe bene sì. Però non ne sono sicuro sull'alluminio di Lewis extra framework, perché la prima è un po' troppo debole quando c'è acqua, c'è sempre acqua, e la seconda cosa, mi sa che fa anche delle reazioni indesiderate. Purtroppo ci sono delle fasce di Lewis che sono proprio quelle che sono i migliori, però non è scontato che funziona. Cioè, per la xilosi direi la zeolita va bene, però l'alluminio credo di no. Quello no. Ci servirebbe... poi, una cosa che funziona anche è l'ossido di stagno. Però ci vuole un ambiente chimico idrofobico. Quando lavori con l'ossido di zinco nanoparticolato, ci vuole un ambiente chimico idrofobico. Non vuoi l'acqua che è nel solvente di arrivare vicino a questo sito. Ma una delle cose più importanti che abbiamo imparato, altro che il catalizzatore, è il solventi. E come il solventi arriva ai siti catalitici. Quella è una delle cose... Quell'esempio della polivinilpirrolidone, noi abbiamo chiamato alla fine di solvente solido, perché cambi proprio la composizione, come si comportano le molecole dentro il materiale o vicino al sito catalitico. Bravo. Dai ragazzi, una domanda.
Io tanto che lo penso. Invece quel catalizzatore a base di niobio, perché noi ne abbiamo lavorato abbastanza con la niobia ultimamente, noi facevamo prevenzione di ossidazione e anche noi vedevamo che quelli che comprati dall'altro generalmente sono poco attivi perché non riesce a controllare gli stati attivi, le dimensioni. Quelli che avete preparato voi, come li avete preparati? Perché ne avete fatto vedere diversi?
Quello lì abbiamo preso il cloruro di niobio e abbiamo cambiato il pH, dovrei chiedere ai miei studenti, però credo pH 2,5, 3, mi sa. Ha precipitato l'ossido, ha lasciato per un po' a temperatura ambiente proprio, poi filtrato, mi sa, precipitazione semplicissima. Adesso mi sa che lui cambia perché abbiamo la ditta brasiliana di niobio fa l'ossido, l'ossalato ammoniacale, quindi abbiamo preso e proviamo a fare da quello, che sarebbe più economico. Il grosso problema nel niobio, nell'osso di niobio, è la trasformazione di fasi. Quindi se hai acqua e alta temperatura, diventa cristallino. Quindi quello che abbiamo fatto parecchi anni fa è stata, quando fai un legame, una legazione fra la silice e l'osso di niobio, tu riesci a controllare questa trasformazione di fasi. Perdi tanto dall'attività catalitica perché se lavori con l'osso di niobio amorfo, con temperature di acqua, diciamo 200 gradi, cambia fasi. Quindi, e se hai una particelle metalliche supportate lì, sono coperte per quello sì. Quindi questo abbiamo fatto per le precipitazioni semplici. E poi abbiamo anche fatto modificato questi materiali con il fosfato per cambiare le proprietà acide di Bronsted.
Voi ragazzi, non siate timidi.
La conversione da grano a furano.
Sì.
È stereospecifica. Cioè, si viene a creare lo stereocentro.
Questa è una bella domanda. No. Per quello che abbiamo fatto, no. Non abbiamo mai studiato se c'è il cambio degli isomeri, ma credo di no. Perché noi lavoriamo con l'OR. Ecco. Però non abbiamo mai guardato se c'è un cambio di isomerizzazione. No, non dovrebbe con quello che lavoriamo noi, ma quello sarebbe una cosa bella da studiare. Ho una collega, professoressa, che lavora proprio con questo tipo di reazioni estere specifiche e lei era interessatissima in guardare proprio quello, quindi sarebbe un punto bellissimo da guardare, appunto. E poi ci sono anche adesso quelli che prendono questi catalizzatori. Di nuovo, questi catalizzatori porosi ci interessano perché sono modelli, sono molto facili da lavorare. Quindi cambiare dentro i gruppi funzionali per quelli, diciamo, per vedere se riescono a controllare la stereoselettività di questi composti. Ma hai ragione. Questa è sarebbe una cosa bella da guardare.
Posso fare un commento?
Sì, posso.
Mi sembra che non ci sia molto.
Volevo semplicemente raccontare la storia di Gian, non so se la sapete, visto che ci ha fatto vedere un po' di storia. Allora, no, dunque, lui ha lavorato qui da noi, come si è visto un po' di immagini. La storia di Gian è la storia di una persona entusiasta. Sì, entusiasta. Allora, di questo mi piace raccontare, al di là del fatto che lui sia qui. perché lui è una persona che per il suo dottorato ci ha messo quasi 5 anni, e non perché era stupido, anzi, ci ha messo 5 anni perché voleva raggiungere un obiettivo che andava al di là degli obiettivi che erano dei suoi. Lui dopo 3 anni aveva dati a bizzeffe, aveva fatto qui alcuni di quei catalizzatori che avete visto, delle silici particolari le ha fatte qua, poi le andate funzionalizzate, ha fatto carboni, ne ha fatte di tutti i tipi, molte cose. Però lui ha raggiunto quello che voleva. Lui dal suo dottorato, lui era un ragazzo brillante come adesso un professore brillante, volevo che si fermasse qui da noi, invece lui aveva un obiettivo, lui gli piaceva questa chimica, gli è sempre piaciuta, che non poteva fare qua, è andato negli Stati Uniti 3 anni, negli Stati Uniti ha imparato a fare questa chimica, è tornato in Brasile. Attenzione che il Brasile, dove è andato lui, non è il paese sottosviluppato, dove è andato lui è l'università più grande del Brasile, che se andate a vedere le attrezzature che hanno, noi ce le sogniamo, soprattutto anche San Carlos, ma soprattutto l'Università di Campinas, da dove lui arrivava. E lui ha fatto il dottorato un po' da noi, molto da noi, un po' in Brasile. Lui ha fatto un dottorato binazionale. Vi invito a sognare, a perseguire le vostre cose e poi anche andare in Brasile. In Brasile trovate, attraverso, adesso studieremo degli accordi di collaborazione, trovate delle università fantastiche, della gente più che fantastica, e quindi ragazzi investite il vostro tempo nel dottorato in cultura e andate, guardatevi in giro per il mondo. Nel mondo non ci sono solo gli Stati Uniti, la Francia, l'Inghilterra, ci sono anche questi paesi che non sono i cosiddetti paesi emergenti, che naturalmente sono paesi emergenti dal punto di vista forse culturale, ma neanche tanto, sono già emersi e ci stanno sommergendo, non fosse altro perché la quantità di petrolio e di gas che trovano ogni anno è infinita, ma sono paesi con altissima cultura. Io credo che sia molto bello questo di avere persone che hanno studiato da noi, che tornano lì, che fanno cultura in parte presa da noi, ma che lì possono trovare uno sviluppo. Lui qui in Italia non aveva nessuna chance, nonostante la sua bravura, le sue capacità. Il Brasile ha trovato un ambiente che ha sfruttato quello che lui ha imparato in giro per il mondo, in Italia e negli Stati Uniti. Quindi complimenti a lui e mi piace questa idea che è uno dei nostri ragazzi che ha fatto fortuna basandosi in parte dalle cose che ha imparato qui. Questo è molto bello. E poi c'è tutto l'aspetto umano che non vi racconto, perché potete immaginarvelo quanto è stato bello il periodo che lui ha passato qui da noi. Grazie Giacomo.
Grazie professore.
Grazie.
Possiamo...
Sì, se non avete altre domande, possiamo subito. Ok, va bene. Allora, grazie Giacomo.
Grazie.